then how do they evaluate the model? What are the different evaluation methods that this generates? So basically, in every experimental folder, it generates a lot of artifacts such as PR curves, F1 score curves, confusion matrix, then some uh, model validation events. Okay. Now, earlier we used to implement all this by our own, but now at least somebody has already done that. You should at least know how to use it. What does this mean to me? Like, what is the practical perspective of what this is? Otherwise, it wouldn't make sense to actually do this course, right? Okay. Uh, all right. So, what we would be continuing is to understand the deep learning era of the image segmentation. See, there are a lot of models in image segmentation, but we don't have the bandwidth to cover each and every model, but you can explore on your own time. But one model that is very, very important to understand and most widely used is a masked RCNN model. Now, this is the last advancement of the RCNN family models. Okay, so RCNN families are the one that started to introduce object detection or localization to the deep learning. And RCNN stands for region convolutional neural network. Okay, and from RCNN we came to fast RCNN. From fast RCNN they made faster RCNN, and faster RCNN is basically for object detection. And then they extended the faster RCNN to also image segmentation, so that in addition to the bounding box estimation and the object classification, they can now also output a mask for every object. Okay. So it is also a two-stage because it is built on top of faster RCNN, and it's almost identical to faster RCNN, at least at the first stage, where it is proposing regions by the region proposal network. So that's why they say we have two stages. The first one is mostly the region proposals. And then in the second stage is where the difference is made between the faster RCNN and the masked RCNN. Where in faster RCNN, it is only trained to output bounding boxes and object classes. But in master RCNN, they add an additional head, okay, where it will be trained to predict the object mask. Okay. So then in order to do that, they added or replaced the previous RY region, which is the region of interest, with another layer called ROI aligned, which means it basically gives a fine-grained alignment to do pixel-to-pixel segmentations. So this was necessary for them in order to do a mask predictions. Okay, so this is very high-level intuitive understanding of what mask RCNN is done. Okay, so this is a sort of an uh, building blocks of mask RCNN. See, it takes images and input, it passes through a series of layers of CNN. So this block is basically your feature extraction layer. Okay. So this is where all those features are learned. And then from the features learned, the RPN, which is region proposal network, it proposes regions where there's a high probability of the object presence. And then there is an ROI alignment layer. This is required because in mass Gaussian we are doing dense prediction, right? At the beginning of this class, we understood what dense prediction means. So dense prediction means for every pixel of the image, we do a prediction. Then we have again, this is also a multitask problem. So in image classification, it has only one task, which is image classification. In object detection, it has two class. One is bounding box and object class. In this, it has three tasks. One is bounding box prediction. Another is object classification. Another is the mask prediction, because it has to give the precise boundary of the object mask. Okay. Both is possible with mask casting. Yeah. Sorry, another. Hmm. Okay. Yeah. So region proposal will gives you the regions. Okay. But it does the ROI align also takes the feature map also in order to align those pixels. Okay. Because it cannot just works on a very region bounding boxes. It also needs this additional data in order to align those ROIs. So that's why there is a connection from here to here. Yes. Sorry, can you be louder? Like CNN has convolution max pooling. That's what I get after that. Huh? Yes, yes. So always the final few layers will be fully connected layers. Yeah, softmax will happen in this classification layer. In CNN. That is the detailed view of it. This is a very high level view of it. If you go into that, it will be more similar to a ResNet kind of architecture. Okay, so ResNet is also one of the key CNN architectures, which is used in all these master CNN, master CNN. So I also highly recommend that you also go and study this ResNet architecture. So there is one book, or it's an online book. It's called DL.ai, I think. Interview, yeah. If I am like an interviewer for image classification, I would ask you about ResNet. Yeah, if you know ResNet, probably you know all others. I, I mean, doesn't make sense to know everything, right? Yeah, I think this one. So this is a good reference, but I'm not sure if still people are. So in this, they explain more things. So CNN starts from fifth CNN, then you have Linet, then you have modern CNNs. Yeah. So in modern CNNs, it started with AlexNet. After AlexNet, VGG was most widely used. Then after that, there was Google Net, Inception, and all those things. Then came this ResNet. So ResNet is what is important to understand. So what ResNet basically says is typically when they designed this CNN architecture, so they always have a block. They present it in blocks. Okay, and each block will have multiple convolution layer, activation layer, max pole layer, like that. Okay. Now what happens is the more the deeper and more the deeper it becomes, at every layer it start losing information. Okay. Now what they did is in order to continue this information passing, it's like they just make a connection to it. They pass the input also as an one of the input to the one of the layers. So they always try to maintain this information. This is a very high level intuitive explanation I'm giving, but I would say that you can read this in order to have a more detailed understanding of it. Same. Yes, this is indeed a skip connection. Yeah, it's basically also a residual connection. Yeah. So when they were trying to build, see, before ResNet came, they were not able to go that deep. After, let's say, 50 layers, if you train a model with 100 layers, the performance start deviating. So then they start to investigate why I'm not able to go deeper. So then they came up with this concept. So ResNet is what probably, if I understood correctly, can go up to 150 layers. 150 layer, 250 layers, those kind of yeah. So it basically starts with ResNet 18, ResNet 52, ResNet 56. There are like different variants of ResNet is there. 1856 is basically the number of layers. Yeah. So if your data set is very small, you just have 100 images of cat, 100 images of dog. If I ask you to train one image classification model, okay, will you select ResNet 18 or ResNet 256 or something, to 152 or whatever? Then probably I would start with ResNet 18 because that's maybe sufficient for a simpler problem. And then if it's a more complex and if the data set size is sufficiently large, then I would go for a bigger model. And not, yeah, the more complex, the more bigger the model. Okay, so then for image classification, this would be sufficient, all if you understand ResNet. So for object classification, if you understand YOLO and faster CNN, that would be sufficient. But there are also modern architectures also there. For example, the detection transformers. Okay, that also is good to know. Okay, then detection transform is a little bit outdated. So recently we called RTDTR. So real-time detection transformers are there. Okay. These are all things that you should know. See, these architectures are already part of Ultralytics. So you can just go and experiment with that. So these are all more modern object detection architectures, which are, you can just classify that CNN based object detections. Then you have transformer based object detections. No, the transformer, no, it's not exactly the same, but the underlying engine, the core concept of it is same. The transformer concept that we will see today. Yes. Okay. So we can skip Okay, so before we go to vision transformers, what look? Ian Goodfellow. Okay, so that one is more detailed, more low-level explanations. Okay. Depends on your quest for knowledge. If you want to more go deep, you can refer that. This one, no? If you have already have an online version, no? You don't need to buy a hard copy of it. Yeah, it's free. D12.ai. So you also have a supported notebooks also here. Okay. This book is good. If you are more of more of a Keras, I think this book is good from Francois. I think this book is also good. Okay. Hmm? Okay. So this is for online. Yeah, I don't think this is. Do we have a okay, paperback is 2,500. Yeah, so first edition. It should have the okay. Yeah, it doesn't have. Okay. Um. Okay, so this then let's come to vision transformers. So Dino is basically some foundational models. Uh, yeah, from Facebook. So those are like also built on top of transformers if I'm not wrong. Yeah. So so there's like uh, Dino V3, those kind of models are there. There is also grounding Dino, which we'll see next week. Uh, Dino V3 is like that. This is what you're referring, right? So these are like, as they mentioned, it's an self-supervised learning for images. So that is another advanced concept called self-supervised learning. So we basically have supervised learning and supervised learning. Then there is another paradigm of how do we approach the model training is a self-supervised learning, which means instead of having explicit labels to train the model, can we use the image itself as a label to train the model? So then what they do is, okay, you have an image. Okay, then what I will do is I will cut this images into 3 cross 9, 3 cross 3, which means I have like a 9 patches. Then I jumble them. Then it becomes like a kid's puzzle. Okay. So then the model has to learn in order to arrange this image in the correct order. Okay. Because I know the order, right? From the image itself, I know the order. So I don't need an explicit labeling. Somebody has to sit and then label this image into one of those categories or draw bounding boxes because these are like pretty expensive and a lot of time consuming. So they came up with another approach of can we use, we have like billions of images, right? But the problem is how do we label these billions of images? So that's why we came up with an approach of can we just train the model just with the images, but without labeling. So that's why this kind of yeah. So that's why this self-supervised learning came. There are different approaches of this self-supervised learning. One is jumble the images, make it into a puzzle, and uh, the, try to train the model to predict the order of these patches. Right, 1, 2, 3, 4, 5. Another could be is that you could just randomly mix up a certain sort of a noise into the image and try the model to predict those noises. There are different approaches of them. And Dino is basically one of those foundational models, which basically was trained on a very large scale images, but without any explicit labeling. Then what they will do is they call this foundational models. You know the concept of foundational models was that sort of touched upon in previous modules, right? Anyway, it was part of the next week's session. So foundation models are typically the approach is to train these models on a very huge, large data set. And the chat GPT, GPT models are all foundational models which are trained on like billions and trillions of data. And they are typically of huge in size. They have billions of parameters. But they do not have any specific task that they are trained on. They do not have any specific tasks such as image classification or object detection or segmentation or video tracking, nothing. All they are learning is the foundational understanding of the image itself. So the GPT is not trained on sentiment analysis or summarization or translation or let's say transcribing, nothing. Previously, NLP used to have same like how I was going through the last couple of days that it has a very task specific models. There will be one model that will do only sentiment analysis. There is one model that will do translation from English to French, French to English. There is one model that can do a topic modeling, which can classify your text into one of those predefined topics. So there were different models. Then the GPT era came that okay, we are not going to train on any specific task. I have like trillions of data in the internet. I'm just going to scrap all the internet and then train one model on very generic task. Okay. And then use this model as a foundational model and then do a downstream task such as sentiment analysis, translation, summarization, all those things. Those are called downstream tasks. So the image classification, object detection, segmentation are downstream tasks. Now, if I have a Dino V3, which is has a foundational understanding, then I can take this as a starting point and then fine tune it on my downstream task, such as image classification. That's basically a high level look at what this kind of models are. So these are the time where um, deep learning was evolving from a very task specific model into a foundational model. Now, whatever the GPTs kind of models, the Llama kind of models are all built on as a continuation of this Dino kind of models. There's also one more model called very important. Have you heard of this? So open a clip, right? So clip is basic. I think I touched upon this in last week. So basically, this is the model where it basically combined the NLP world and the vision world. So previously they were like considered as two different areas. And then when the transformers came, all of these NLP models, they were using these transformers as their core blocks. And it was giving very excellent results. It was giving magical results when they moved from when they moved towards transformers. And then there was like sort of a vision vision advancements was a bit lagging because they were all based on CNNs. And these NLP guys, they were advancing at a blazing fast with transformers. They were just doing some clear breakthroughs. So then this vision scientist, they try to inspire from the NLP guys, which is basically the transformers, and then they say, hey, how can we apply transformer to vision? But it was not very straightforward because can someone say why? So, okay, before that, is transformers already covered in your NLP course? Okay. So high level, how transformers works? Can someone say? What's the NLP part? Computer in class, they have some output by translation. So English, yeah, yeah, perfect. Too much. But so, oh, let's say, I just want to always think as an intuitive practical way. Can I apply CNN models on text translation from English to French, French to English? Models combination between text. Yeah, why? Sorry? Combination is nothing for text is still very. Yeah. Yeah, I think you're getting it. Can I then apply RNN or LSTM on image classification? So, so it is for text, right? But then why is that? So there is a one particular word I'm trying to get. So basically, which means that their task is fundamentally they are different. So in image classifications, basically the input is an image and output is a sort of a class prediction, right? Similarly for the objection, but for sentiment analysis, leave it. But let's say for translation, what is your input? What is your output? It's context. Yeah, I know input is some English text and output is French text, but how do we sort of yeah, okay. So it's basically a sequence of words. That's how. So it doesn't know it is English. It doesn't know it is French. Model is dumb actually. All it knows is that hey, these guys are feeding me some sort of an bunch of words, but those bunch of words are not just dumped in a random way. They have an order to it. Okay? But for image, there is no any specific order. So it just converts it and just compress those information into a low dimensional space. It's basically a dimensionality reduction and basically the projection of data into low dimensional space. I have to see how it's basically sort of an advanced PCA. But for text, it's basically they call it it's a sequence to sequence problem, right? So basically you are saying I'm passing a sequence of words into a model, and then you are saying give me a sequence of words which is in another language, right? Now, can I, how do I take an image and see transformers? They expect a sequence of words. Okay. Maybe you can just remove that words, but it expects a sequence of a data, order of data. But if you see, imagine an image, it is not a sequence of pixels, right? Can I just put, if I want to feed in an image into a transformer, then I have to feed all these pixels from 1 to 1 million pixels in an order, because it just takes a sequence of tokens. So then how would I then, that is where the problem that, okay, transformers powerful because they have a very powerful concept called attention. But that one is, I'm not able to directly apply to my images because my images is not a sequence of tokens. They are just a 2D spatial information. Now, how do I convert this 2D spatial information into a sequence of tokens so that I can feed into a transformer? Unless I figure that out, I wouldn't be able to apply transformers to image. That's basically what these Google researchers figured out. Yeah. To the transformers. Yeah, but that will be very raw pixel values, which is like 1 million pixel values. The image space, if you project each pixel into a sort of hyper dimensional space, it's so huge that you cannot handle it within your own single computer. You might need a supercomputer. That is why we are doing all this dimensionality reduction using CNN convolutional operations. But in transformers, if you roll out all these, see in the final whatever you're saying, it is achieved after passing through all these. So you go from 1 million data points to 512 data points. Okay. Now, the way I did this, I did a very efficient data compression through convolution. But how do I do this for the transformer input? How do I convert this 1 million pixels into I cannot feed 1 million pixels directly to a transformer input layer because it expects maximum 512 at a time. So yes, transformer is still a sequential model, and but it does it much more effectively and efficiently than the LSTM and RMN models. So there are two major categories of models, right? One is the CNN models. Another, all your NLP models are sequence to sequence models. Right? It takes a sequence of words and it predicts a sequence of words. So RNN also, it takes a sequence of words and then you feed it a sequence of words, sequence of words, sequence of words, and gives you some certain output. Same also LSTM. Same also transform. Hmm. No, no, no. I think you are confusing. So that is different. So we are not talking about parallelization. We are talking about the data structure, a data unit structure itself. By nature, natural language processing, right? That area, the text, the words we are speaking, all are sequential in nature. They have order, but images doesn't have an order. It has a 2D space. In text, we are in a one-dimensional flat space. You have a order of words. You have order of sentences making a paragraph. You have an order of paragraph making a page. You have an order of page making a textbook. Right. So yeah, another word I think he mentioned correctly is the text is more structured, but image is unstructured. So that is where in 2021 they released this paper called Vision Transformers. This is also one of the important papers that you can go through. So we understood what is the challenge of applying a transformer to an image. Okay. And then this Google researchers, they figured this out. How do we effectively and efficiently apply the transformers to the images? So what they did is they come up with this sort of patch encodings, which means they divided the images into patches. And then they consider this each patch as one tokens. Okay. So then see here you will have a sort of a 9 tokens. Then this would then be projected into a sort of a linear neural network in order to get some sort of a 512 embedding vector for each patch you make it. Then you can then arrange all this patch embedding vector, concatenate them, and then feed it into further layers. Okay. In that way, the transformer was able to take in the image as an input. You are not directly feeding an image into a transformer. You do some patches and convert that patch into patch embeddings. Then you add positional information of these patches into those patch embeddings and then feed that into the further layers of the transformers. Then you can apply all those attention, multi-get attention onto your images. Okay. So this is hmm? No, it's just a linear neural network we can add. Okay. So that also will be learned to the tree. So you divide them into certain patches and then produce low dimensional linear embeddings. It is not any convolutional operation is being done here, or we are not doing any feature extractions here. All we are doing is just converting into some low dimensional feature embeddings. No, not tokens. So your so each patch is a token. So like how you have yeah. So each patch, if you then project it into some linear neural network, linear layer, that can take in the raw patch pixel values and convert that into a 512 embedding vector. You understand? Yeah. Yeah. So let's say each pixel, each patch is of let's say 9 cross 9. Okay. Which means you have 81 pixel values, 0, um, 0 to 255 RGB values. Those are then fed into a linear layer, which is nothing but a fully connected layer. There will be like neurons that are connected to each other, right? It's basically called linear layer. Then that basically it's converts this patches, raw patch values into a embedding values. Okay. Now, how that converts that, it will learn during the training. But initially, it would just do some random conversion. But During training, it will learn to convert that into a embedding properly that's fitted to execute this task of image classification. So these are the 7 steps of the VAD, right? First is to split the image into patches like 1, 2, 3, 4, 5, 6, 7, 8, 9. Then flatten the patches, okay, and then project them through some linear networks and then create some low dimensional linear embeddings and then add some positional intelligence into it. Feed this sequence as an input to a standard transformer encoder and then pre-train the model with the image labels and then fine tune on the downstream dataset for image classification. Okay. So does this vision transformer is exactly the same as the transformers that is used in image translation or what is the major difference here? Uh, yeah, processing is different, but there is also one big difference between this vision transformers and the transformers. Um, so in transformer, he mentioned there is something called encoder and decoder. So in this, there is no decoder. Okay. Um, so you know the encoder decoder model, what they do. Like, so I'm just explaining at a very high level, but so basically like an encoder decoder model is have an input. Yeah, but I don't want to go into all this fancy names, but I'm just trying to bring you the fundamentals. You might have, if you type encoder decoder, you might find these kind of images in the Google search. Okay. Now this is your input, right? This is your encoder. This is your latent intermediate. This is your decoder. This is your This is how the encoder the decoder architecture works. Right? So what is the job of this encoder? First, conversion and if you doing that, can change how it works. Yeah. High level, it basically encodes the uh, information of this input into a lower dimensional space. So this might be a very high dimensional space, right? Now this would be just a 512 vector, which means it projected everything into a very low dimension, compressed and it encodes all those information into a low dimension. Now, in order to do image classification, right? In CNN also we would do a similar thing. So we take an image, right? And then we pass this on to a CNN. Imagine that this is a CNN. So what it takes, this is an image, passes into a CNN, and then finally what it gets a feature map. A very low dimensional feature map. Then you flatten it, then you will get the vector, right? It's a feature vector, we can say. Then you have like fully connected layers. See, and finally you have your classification layer, which will tell you what class it is, whether it is a cat log percentages. So now this, I need to come to this feature map, right? Or feature map. This is basically my latent space. There is sort of a technical term. So we come to a latent space, and this is where we can do this image classification. I cannot do image classification directly on the image. I cannot do any operation directly on the input. I somehow have to map the input to a latent low dimensional space. And then I can only do classification or any type of task only on the latent low dimensional space. So for transformer, typically they are a encoder decoder model, because if you see the NLP task, they have to go from English to French. So I went from English. So this is my English. This is my raw text. From that, I went into a latent space. This is just a numerical representation. I cannot figure out anything from this. It is just a bunch of numbers. But now from this bunch of numbers, I have to go to French, right? Then that is where the decoder comes. So it basically takes a bunch of numbers, which is a vector, and then I have to decode all the informations that are compressed into these vectors, and then I figure out that I have to come up with this French text. That is basically the task of translation, right? But for my image, I don't need this decoding part. I just need this latent space. From there, I can then connect it to some FCN similar to, I will take this block. Okay, I put it into, connect it to this block, and I will get my classification. So that's why vision transformers for image classification is just an encoder only model. Okay, so we don't need a decoder for that. So that's why if you see, right, once that it passes through the transformer encoder, oh, sorry, all it needs is MLP head. MLP head is nothing but this FCN, multi-layer perceptron. They have different names. So this is nothing but a multi-layer perceptron, or you can call it as fully connected network, or you can call it linear network. There are different names. Okay. Okay, that's a very good question. So if you look at the practical aspect of it, uh, so the vision transformers, right? Although they are the advancements of the deep learning thing, and there are like a lot of reasons why we want to go in this direction, but it is not always a practical choice. Okay, if you have a small data set and if you want to train an image classification model, okay, maybe the vision transformers are not always the best. They have fundamental limitations that they require a lot of data to train the model to a sufficient accuracy. So if you compare transformers to CNN, transformers are more data hungry than the CNNs. So you can just build a very reliable, accurate model with a relatively lower data set size with CNN than the transformers. Example. So take for example the Cipher 10 data set. If you train it from scratch, you just give a try. Don't take any pre-trained models. If you have this only some 1,000 images and you have 100 examples for each class, Cipher 10 is a 10 class model. Now, if you train it from scratch, a CNN would get trained it in a relatively less epochs than a vision transformer. And it would be outperforming vision transformers with lesser training than the vision transformers. Okay. Now vision transformers will outperform CNN probably in image net kind of data set where you have 1,000 classes and each one has totally millions or billions of images. Okay. In that, probably vision transformers can outperform CNN. You understand now, right? Huh? Yeah, more data hungry. If you have a very small compact data set, right? Probably CNN is better than vision transformers. So, for example, if you are doing some medical uh, disease classification, such as types of pneumonia classification. In pneumonia, I remember there are different types of pneumonias out there. And let's say you have only 50 images per pneumonia type. Hmm? So totally, let's say 10 pneumonias are there. You totally have only 10 into 500 images only there. And you cannot use a pre-trained model because it's a completely different domain. You're going to take a model that is trained on internet images and train a medical spot, right? So you would be training it from scratch. So this is a classic example. Okay. Okay, maybe after lunch we can come and continue the rest of the things. What time is the lunch? 1 o'clock. Okay, wait 4 minutes. So clip is one of the very important model that was built on top of transformers. Okay. We can read this blog for the rest of the 8 minutes. So what they're saying is we are introducing a neural network called CLIP, which is connecting language, basically text and images. Basically, it's contrastive learning, if I remember. CLIP stands for. uh, Let me open the paper. Okay. Yeah, yeah, yeah. Yeah, yeah, yeah. Yeah, yeah. So yeah, you that is a very good question. So now, so transformers, they use this attention mechanism to understand basically the global context of the sentences or the paragraph that you use. So earlier, the LSTM or an they had a very small focus area. So they will understand only few words from left, few words from the right, but they do not understand the whole context of that full sentences or the things, right? So now they already have, right, the animal, some examples are that I don't remember that. So based on the context, the next word will change, right? So similarly for image also, we have local context and we have a global context. Now CNNs, when they do this sort of processing, so they only look at a very local region. So when they look at the top left of the image, they doesn't know what is in the bottom right of the image. So, but sometimes whatever is there in the rest of the image, it helps to actually do a better classification or identification. And that is where this attention mechanism is coming. And applying those sort of a global context to image also helps the model learn better. Okay. So see, although deep learning has revolutionized computer vision, current approaches have several major problems, or labor intensive to create. Basically, they are talking about labeling, and also that previously what they do, how do they approach this? They trained one model for one specific task. So that's why they say standard vision models are good at one specific task. And when you want to train another model for another task, it is basically very time consuming. So then they came up with, can we have a zero shot capability, similar to, they also inspired from GPTs. Okay. Now GPT and GPT-3 at that time, they had a zero shot capabilities, which means that you could just prompt the model without being the model trained on that specific task, and the model has the capability to learn the intention of your ask, and it would give you the correct prediction. Okay. Um, those kind of capability was demonstrated using GPT models, and GPT uses transformers. And then they basically challenged them, can we bring zero shot capabilities into vision? Right. Uh, that is where they came up with this contrastive language image pre-training. So again, this is another technical term that you should be aware of. Pre-training means it is training a model not on a very specific task. It is just learning the foundational concepts. Once you pre-train a model, then you fine-tune that model on a downstream task. Okay? This is how it you should look at. So how they did is they had a huge data set. So they had a image text pairs. Okay? So they have, let's say, billion images, and for every image, they also have a corresponding text caption or a text description. Now, these are all scrapped from internet, right? So if we go to internet, we have an image. They also have some sort of a text description in it. So they scrapped everything, and they have an image text pair. Okay? Now they want to train a model in a self-supervised way, which means that they take the text caption as a sort of a supervision to train the image model. Okay. So how do they do it? They do it in a contrastive learning, which means they will take a batch of images from I1, I2, I3 all the way up to IN. So there are n images, and they have n corresponding text. Okay. Now we pass all of these images through an image encoder. The same thing what I did. When you pass an image through an image encoder, what you get? We get image embeddings. When you pass a text into a text encoder, what you get? You get text embeddings. So you have image embeddings, you have text embeddings. Now you can see this, right? So you have n cross n matrix. Okay. Now the job of this model is to adjust these embeddings in such a way that the similarity between I1 and T1 is high, because that is a pair, right? The text description of this image is basically the T1 is mapped to I1, T2 is mapped to I2, okay? Which means If I compare or calculate a cosine similarity between I1 and T1, which are nothing but an embedding, you can easily calculate a cosine similarity between two embeddings. The cosine similarity between I1 and T1 should be maximum, and cosine similarity between I1 and T2, T3, T whatever, etc. should be as minimum as possible, which means the diagonal value, right? It should be maximum and the off diagonal value should be close to zero. Okay, this is called contrastive learning. Okay, so then with this, if you understand this diagram, then you understand clip. Then they train these models in this fashion. At the end of the training, if you compare a batch of image with its corresponding batch of text, you will get a high similarity in the diagonals and a very low similarity in the off diagonals, which means your image and text are aligned. Okay, so you can go from image to text. If you go put one image and ask the clip model describe this image, it will give you a very good image description. If you ask compare, if you give a text input and find the relevant closest image from my image database, it will fetch you the very close similar image of this text. Exactly. Yeah. So that's what she said. During inference, if I in my search box, right, if I just type uh, a teddy bear of let's certain brown color with certain description. Okay, if we have a set lot of teddy bear images, then it converts this text that you have entered into your search bar, convert that into an embedding. Then it will also convert all the images in your database into an embedding. It compares the cosine similarity between this, and whichever has the highest similarity, it will retrieve that image and show it to you, and it will be the very close similarity to your text. Okay. Yeah, that's basically clip. So clip is a very, very important model. This is one of the first model that started into Gen AI. Okay. Okay, then let's break for lunch and come back. Thank you.